Now that you know how a diode works, we can discuss the electrical characteristics of a solar cell. We will do this using the current versus voltage, or IV curve, as well as the power versus voltage, or PV curve. We will discuss the key electrical parameters of a solar cell, namely the ISC, VOC, IMPP, VMPP, and finally, the fill factor. Finally, we are going to show how these curves change with irradiance and temperature. Let's start with the behavior of a diode in the dark. This is the symbol for a diode used in circuit diagrams. The IV curve of a PN diode looks like this. Voltages below a certain threshold result in very little current flow, but for voltages above this threshold, the current rises exponentially. We can model the IV curve of a diode using the Shockley equation. It describes the current through a diode, I, as a function of the voltage applied to the diode, V. I is the y-axis in the plot above, and V is the x-axis. For large voltages, the exponential term will dominate. Vt is called the thermal voltage and depends on the cell temperature. It is around 26 millivolts at room temperature. Gamma represents the ideality factor of the diode. This value is intrinsic to the diode and does not change based on external conditions. A value of 1 represents an ideal diode, while a larger value leads to a shift of the exponential shape as observed in the real world. For negative voltages, the exponential term will become negligible, and there remains a very small negative current. We call this the saturation current, which is usually written as I0 and pronounced I0. The current is on the order of pico, that's 10 to the minus 12, or even femto, 10 to the minus 15 amps. If we zoom in, we can see that here. A solar cell is a diode, so this IV characteristic is exactly how a solar cell will operate in the dark. In order to model an illuminated solar cell, we have to add a current source that describes the photocurrent. When we add a current source in parallel with the diode, we have the representation of an ideal solar cell. To make things simple, let's have this solar cell power a resistor as a load. Let's look at the currents in this circuit. Firstly, there is the current coming from the current source. This is the current that is produced by the sun's photons. We call that the photocurrent and use IPH to label it in red here. Some of that current is lost as it travels through the diode in the circuit. We call this the diode current and use ID as a label in green. Finally, the difference between these two currents is the current through the resistor. This is the current involved in the output power of the solar cell. We will call this current I and show it in blue. We will label the voltage across the resistor V and also show that in blue. Let's plot these currents. Here you can see the plots of all the currents of the ideal solar cell model. The photocurrent can be modeled by a straight line. The diode current is the same plot we showed you at the beginning of this lecture, but now in green. When we sum these two currents together, we get the solar cell current in blue. We consider the photocurrent to be positive and the diode current to be a loss, so we're going to invert this plot. This leads to the typical IV curve of a solar cell. We have the photocurrent in red, the diode current in green, and the sum of both curves in blue is the IV characteristic of the solar cell. There are three important points on this plot that are used to characterize the performance of a solar cell. The first point is the open circuit voltage, or VOC. This is the voltage when the solar cell is operating at zero current. We call it open circuit because this is the voltage you would measure if the solar cell's terminals were open. The second one is the short circuit current, named ISC. It is the current generated when the terminals are short-circuited. This corresponds to the photocurrent. To see the third important point, we need to look at the power produced by the solar cell. Power is the product of the current times the voltage. We can draw this power as a function of the voltage. When doing that, we get the PV curve of a solar cell, as shown here in orange. At both the VOC and the ISC points, the power is null. The maximum point on this curve is called the maximum power point, or MPP. This maximum power point occurs at a given voltage, which we call VMPP. This VMPP voltage corresponds to a current IMPP on the IV curve. The point PMPP, equal to VMPP times IMPP, is the third important point used for the characterization of a solar cell. Operating at PMPP generates the most power possible given the irradiance conditions. The fill factor is a popular parameter for describing solar cells and modules, even though it is useless when modeling PV cells and modules at the system level. Fill factor is defined as the ratio of the IMPP times VMPP to the product ISC times VOC. This is illustrated in this plot, where fill factor is the ratio of the area of the orange rectangle, which represents PMPP, to the area of the blue rectangle. The fill factor is sometimes used by some people for the evaluation or the comparison of the quality of a cell. The higher the fill factor, the more rectangular the IV curve. We do not do this at PVsyst, as fill factor is not directly related to the PV cell efficiency. Furthermore, we've observed that some manufacturers manipulate the VOC value to get a better fill factor in their datasheets. So now we know what the IV and PV curves of a solar cell look like. The shape of the IV and PV curves of PV modules have the same shape as individual PV cells. The voltages on the IV curve are just multiplied by the number of cells in series. How do these curves change with different external conditions, that is, the irradiance and the cell's temperature? In PVsyst, this behavior is fully described by the one diode model. Here, I will just show you the qualitative changes to the curves. These are the IV and PV curves of a module at different irradiances obtained by PVsyst. The first plot shows that the current is proportional to the irradiance. The irradiance does not significantly impact the voltage, however. Therefore, be careful when working in the field, as a PV module or array of modules will deliver its nominal voltage under a very low light intensity. So as irradiance on a module increases, the power output of the module increases as well by the same factor. These are the IV and PV curves, keeping irradiance constant but varying the temperature. The temperature behavior is a basic property of the Shockley diode model. You can observe that the temperature essentially affects the voltage almost without impacting the current ISC. As temperature increases, the most significant impact is a shift of the entire IV curve to the left, which reduces the maximum power output of the PV module and decreases VOC. This power output reduction is on the order of negative 0.35 to negative 0.40% per degree for crystalline silicon modules. So, for example, under the same solar illumination of 1000 watts per square meter, a module operating at 60 degrees Celsius would produce 12 to 14% less power than if it were operating at the standard test conditions of 25 degrees Celsius. The ISC slightly increases at the same time, but this does not have a significant impact on the power output of the module. We have discussed the IV and PV curves of a solar cell. We also explained terms like VOC, ISC, IMPP, VMPP, and fill factor. Then we demonstrated how these curves change according to irradiance and cell temperature. The ISC will be affected by irradiance, and the VOC will will be affected by the temperature.